Is by Giansiracusa from Swansea, and you are going to talk, if you do not change your title, modular spaces of geometric structures on surfaces and modular operads.
Thanks. Thanks for having me here. So, as a topologist, I like to study spaces, and there are some interesting spaces out there, like the moduli space of curves. Or moduli space of Riemann surfaces. And right now, the G is the genus, and the N is the number of marked points. So this is an interesting space, but as a topologist, you're not satisfied with knowing that a space exists. You want to know something about its structure, either what is its homotopy, homology, or how is it made? How is it built up from simpler pieces? And of course, the two questions are related to each other. So in particular, it's nice if you can have some sort of combinatorial description for this object. And it turns out that there is a nice combinatorial description. Probably many of you have heard of this. It's the ribbon graph model. So this is something which goes back to lots of people. So Mumford, Hare had some role in this. Kontsevich. I should probably say Penner also, and there are probably some other people who I'm leaving off here. So there exists a cell decomposition, not of the moduli space itself, but of MGN crossed. First what? Oh, Thurston, yes. Sorry, I thought you were saying the first one. Yeah, okay, so there exists a cell decomposition of the moduli space crossed with a bit of extra space here, a Euclidean space, which we think of as some weights attached to the marked points. And the cells correspond to ribbon graphs. So the coordinates on each cell are, you can think of as lengths attached to all of the edges. And there's one cell for each isomorphism class of ribbon graphs. So what else did I want to say about this? So this decomposition comes from, well, in the complex view, this comes from Strabel differentials. So you can look at the trajectories of Strabel differentials to draw a ribbon graph on your surface. And you can recover the conformal structure or the complex structure from the lengths of the edges on this ribbon graph. Or that you get it a slightly different way in the hyperbolic point of view. But you get a cell decomposition corresponding to ribbon graphs. But this cell decomposition isn't compatible with any sort of operatic structure. And so what I like to do is put moduli spaces together like they're an operad. So there's another point of view. Oh, but before I get to the other point of view, I should say the cell decomposition is, of course, not just a curiosity. It's very useful. You can do things like compute homology or Euler characteristic. And so applications of this were, for instance, the computation of the Euler characteristic of MGN by Hare and Zagier. So implicitly in this, ribbon graphs were appearing. And then also Kontsevich's proof of Witten's conjecture. On the intersection numbers of these psi classes on the Deligne-Mumford compactification. So there are some nice applications, and there are lots more applications. But this ribbon graph structure is not compatible with the operad structure. I haven't told you what operad structure yet, because the operad structure isn't on these moduli spaces with marked points. It's on moduli spaces with some kinds of boundaries. But there is a different ribbon graph structure that is compatible with the operad structure. And this goes back to Costello, what he calls a dual ribbon graph picture. So in Costello's picture, we don't actually have a cell complex that's homeomorphic to the moduli space or the moduli space crossed with something. Instead, we have just a homotopy equivalence. So what Costello did is he said, let's let Mn be the moduli space of surfaces of whatever genus you want with boundary. And they're going to be n intervals disjoint on the boundary. So I'll call these n marked intervals on the boundary. So the sorts of surfaces you can have would be something like something like this, where here I'll number the boundaries. There's 1, 2, 3, 4, 5. So the marked boundaries don't have to be all in the same component of the boundary. There can be multiple boundary components. There could be some boundary components which don't have any marked boundary intervals, and you can have whatever genus you want surfaces. But now these moduli spaces form what's called a modular operad. So a modular operad is a slight generalization of an operad, where you're allowed to do two things that you can't do with an operad. So an operad is a collection of abstract operations, things which have some number of inputs and an output. To say that it's a modular operad is to say that, first of all, I forget the distinction between inputs and outputs. So the fact that this guy is drawn down here and these are up here is irrelevant now. There's effectively no distinction between input and output. Whichever terminal you want, you can decide to call the output. And then the other thing you're allowed to do is pick two terminals and do a self-gluing. So I can do gluings like this. I can do self-gluings, and I can glue things on the top to other things on the top. So that's what a modular operad is. And these moduli spaces of surfaces obviously will form such a modular operad, because I can glue any one of my marked intervals on the boundary to any other marked interval on the same surface or on a different surface. So inside this moduli space operad of Costello here, although it doesn't really go back to him. Inside M is a much smaller object, which I'll call D, which is the moduli spaces. Why is this chalk squeaking so much for me and not for anybody else? This is the moduli spaces of disks. So I only allow those surfaces where I have something like this. I have something which is topologically a disk, and I have some marked boundaries on it. And if I'm working smoothly, then probably I need to be careful and say in both of these pictures that there are corners there, so when I glue these things, I still get a smooth surface. But I'm really just interested in the homotopy types here, and actually that's kind of an irrelevant point. So inside these moduli spaces, I have much smaller moduli spaces of disks. Now, the big moduli spaces, arbitrary genus, arbitrary topological type, those formed a modular operad. These smaller guys, they don't form a modular operad because if I take one boundary on a disk and another boundary and I glue them together, well, what I have, it may or may not have higher genus, and it may or may not have some holes in it now. So, so you don't have self-gluings on these guys, but you still have the fact that there's no distinction between input and output. So these form what's called a cyclic operad. So a cyclic operad is just like an operad, but there's no distinction between inputs and outputs. Now, Costello proved this very nice geometric theorem which says this cyclic operad of disks freely generates the modular operad of moduli spaces in a homotopical sense. So to make that more precise, what I mean is there's a construction called the modular envelope, which takes a cyclic operad and freely generates a modular operad from it. And when I say homotopical sense, what I mean is I don't want to just take the modular envelope. I want the derived version of the homotopy invariant version of this construction. So what I mean is that the derived modular envelope of D is M. So there's a very concise way to state this theorem. Now, this theorem had some nice applications. So one of the applications was Costello showed that open, what he called topological conformal field theories, but these days we realize that calling it conformal is sort of misleading, and it's just a kind of topological field theory. Open TCFTs are equivalent to what Costello called Calabi-Yau or Frobenius. A-infinity algebras. So A-infinity algebras equipped with a self-duality. And the reason this is true is because an open TCFT means essentially something which is an algebra over M. And to say that it's an algebra over M and M is entirely generated by D is to say that the part of the structure coming from the action of D entirely determines all of the higher genus structure. And the part of the structure coming from D is just an A-infinity algebra structure. So I should have said over here that this operad D is a model of a cyclic model of the A-infinity operad. So this is an immediate application of this modular envelope theorem. And then the second application is not quite as direct, but Costello then considers the universal extension of an open theory to what's called an open-closed theory, where you have intervals as boundaries and circles. So I'll just say, so the universal open-closed extension of an open theory, I'll call it phi, has value on S1 equal to the Hochschild homology of the algebra phi, so the A-infinity algebra. So if I have an open theory, the A-infinity algebra associated with phi is its value on an interval. And the value I get on a circle of its open-closed extension turns out to be the Hochschild homology of the algebra appearing in the open part. So the open part is a priori just an open TCFT, but the first part of the theorem says actually that's entirely determined by just being a Calabi-Yau A-infinity algebra. And the closed part of the theory is the Hochschild homology of the open part. So the second theorem takes a bit of geometric work, a little bit of looking to see that what you get is actually a Hochschild complex. But it essentially follows from this modular envelope theorem, or some variation on it. Further applications of this are, well, since we're seeing the Hochschild homology of some A-infinity algebra, we get moduli spaces of closed surfaces, or surfaces with circle boundaries acting on this, and you get a kind of Deligne conjecture. So you get not the ordinary Deligne conjecture, but a higher genus and cyclic version.
Don't you mean the Hochschild chains, not the Hochschild homology?
Yeah, I should say. Hochschild chains there, strictly speaking. So you get especially if I want to talk about the Deligne conjecture in the next line, yes. So I get a higher genus or Costello gets a higher genus and cyclic version of the Deligne conjecture from this, which says that the chains on the moduli spaces of Riemann surfaces with closed boundaries as a prop, essentially, acts on the Hochschild chains of a Frobenius algebra, an A-infinity Calabi-Yau algebra. And then there's also an application to describing the string topology structure here. So this falls under what Natalie referred to as the past. So the state of the art has advanced quite a bit. So the proof of this very much relied on the geometry of moduli spaces. So the differential geometry and the differential topology of them. And what I want to do is think about a version of this theorem that works much more generally, not just for moduli spaces of surfaces with a complex structure, but a much broader class of geometric structures on surfaces.
Just before you go on, can I ask, in relation to Natalie's talk, could I say that yesterday she was studying not the case where D is A infinity, but E infinity, a cyclic version of E infinity, goal?
So when we...
Associative. I mean,
but then there are no other operations. That's Costello's theorem. You can't find other operations unless you're using something else about the algebraic structure of the thing you're starting with. If it's just exactly an A infinity algebra within the product, there can't be any other operations. That's what. So you must be using something else about the. No.
Instead of A, I mean.
No, they're the same thing in homotopy theory.
But I'm saying not as. I mean,
I think I agree with what you're about to say, Natalie. Yeah, so when Natalie said commutative Sullivan diagrams instead of the ribbon version of Sullivan diagrams, that was sort of hinting at moving from something like A infinity to E infinity.
But she already yesterday found operations that would not exist in general for the.
Yeah, so that's why this is the past.
You must be using something about those algebras that they're not just associative.
I'm saying the strictness of the associative is collapsing some things, which creates higher operations, which you don't have there. By doing this extra collapse, I mean,
so
you were saying it follows, but I mean, you're saying ... I mean, you know, it's not like everything is. It's not. I mean, replacing A infinity by associative changes things. I mean, even though they were.
Yeah. So maybe we could say what Natalie said is that when she starts with a strict associative, then a lot of this collapses, but she gets secondary operations, which is what she was showing us.
But that can also be formulated then in homotopy theory by talking about the, I mean, there are secondary operations captured by A-infinity algebras. This is a question of formality. So you're not using in any way, like any coherent, no Browder operations, nothing, or the vanishing thereof.
Maybe we should discuss this afterwards. Okay, so let me tell you what sort of geometric structure I want. So psi is going to be a sheaf of spaces, or it may be better, I should think of this as a sheaf of homotopy types on surfaces. So what I mean is to each piece of a surface, I associate a space, which is the space of geometric structures of some sort on that surface. So I have something like a sheaf of homotopy types. But what I want is that this is going to send push-outs, not necessarily to strict pullback diagrams, but to homotopy pullbacks. So maybe the fancy terminology for this sort of thing is, I suppose people might call this something like an infinity stack. I want a sheaf of infinity groupoids or a sheaf of homotopy types. So what I'm going to think of this as doing is telling me, given a piece of a surface, what is the space of geometric structures of whatever type I'm considering on that surface. And now I want to make one assumption, which isn't necessary, but will simplify the discussion a bit. I'm going to assume that the space of geometric structures on a disk is connected and I'm going to pick some base point in it, just to be concrete. If this space were to have multiple connected components, then I would instead maybe choose one base point in each component, and I'd end up talking about colored operads instead of operads with a single color. But I'm going to keep things simple and just use one color today. I think Witten once said he was going to keep things simple and just use one brain today. So associated to this notion of geometric structure is a notion of the moduli space. So this is the disjoint union over all classes of surfaces of the space of structures on that surface modulo the diffeomorphism group of that surface. And let me give this a name. I'll call it M psi. So this is the moduli space of surfaces equipped with a psi structure. And I should probably say this is actually a homotopy quotient here. I'm not going to do anything that's a strict construction. All of my constructions are homotopy constructions. So this gives you a moduli space, but I haven't said anything about boundaries and gluing, so it's not an operad yet. We can make it into an operad if we give ourselves some marked boundaries. So we give ourselves some marked boundaries, and I need to specify a little bit of extra data, which is a trivialization on the boundary. All right, M psi n for the disjoint union over surfaces sigma with n marked boundary intervals. And I want to take not the space of structures modulo diffeomorphism. I need the space of structures equipped with, up to homotopy, a trivialization on each of the marked boundaries. So I'll write this psi hat of sigma modulo diff of sigma. And implicitly here, diffeomorphisms of a surface with marked boundary have to fix each of the marked boundaries pointwise. I won't bother encumbering the notation with anything to symbolize that. But what is psi hat? Psi hat of a surface will be the homotopy fiber of the map from psi of the surface to psi of the marked boundary. So this is the space of structures on the surface together with a path from whatever that structure is on a germ. When I say the marked boundary, I mean a germ of the mark, or a little neighborhood of the marked boundary. So I'm giving the space of structures on the surface together with, at each boundary interval, a path from the structure I have there to my base point, the trivialized structure. So I'm giving up to homotopy a trivialization of my structure on each marked boundary component. Okay, now these things, by gluing, these form a modular operad. So if I have one piece of surface and here's a boundary component, here's another marked boundary component, when I glue these together, well, I have the structures don't necessarily agree on the nose, but I have a path to the base point structure. So I can use that path coming from this side and from this side to connect these up on a little infinitesimally long strip and give myself a structure on the whole thing up to homotopy. So these moduli spaces form a modular operad, and inside I have the much smaller cyclic operad of moduli spaces of disks. Okay, now the theorem is the exact analog of Costello's theorem, but now I'm talking about things which are potentially much more floppy than actual complex structures. So the theorem is the derived modular envelope of this operad of disks is homotopy equivalent to the full modular operad of moduli spaces in higher genus. So it's exactly the analog of Costello's theorem here. I'm saying that the moduli spaces of disks in a homotopical sense freely generate all the higher genus moduli spaces. But now my structures are significantly more general than just complex structures.
Are you going to say what you mean exactly by this, right?
Yeah, that comes next. So I should, before, it doesn't come quite next, before I say that, I want to give examples of what sort of structures I'm thinking of here. So what sort of spaces of structures could I think about? Well, I could take psi to be just a point, and then the theorem is saying that the moduli space of structures with this trivial structure is, well, it's the modular envelope of the associative operad. This is Costello's theorem, so it's the space of ribbon graphs. Right, so this is because d psi is, well, I guess it's just the associative operad now. Okay, so that's That's nothing new. This is just Costello's theorem here. You look concerned, Natalie? Well, yeah.
It's the same
Yeah.
operad. We're doing homotopy theory.
Are you?
I'm answering Natalie.
Oh, okay.
It's the same. There's no difference.
Psi is also isotopian, assumed to be isotopian there, right?
Yeah. So this site of surfaces, I'm thinking of that as a topological category, and I want to say psi is not just a functor, but a continuous functor. Yeah. Yeah. So it's very similar to the sorts of things you're thinking of. Okay. So this is Costello's original example, essentially. But I could do something else, like I could take psi to be the space of G bundles. If you want a concrete model for this, you can use that functor, for instance. So if psi associates to a surface the space of principal G bundles on it, then in this case, d psi of n, well, it turns out to be this operad that's called G underbar. It's equivalent to this thing called the G underbar. So in arity n, I have G to the n minus 1, which I think of as G to the n modulo the diagonal action of G. That's this thing here. That's the definition. Right, so it's as an operad in arity n, in operatic arity n, it's just n copies of the group. And when you compose, you're just multiplying group elements. Except secretly, that's actually a cyclic operad, because I think of G n minus 1 as G to the n modulo the diagonal. So the reason for this is because if I have, say, a disk with 3 boundaries, I have a trivialization of my G bundle on each one of these boundary components, and I have some holonomy along each one of the edges. So if I have 3 boundary components, I have 3 holonomies, but then I can take an automorphism of the whole thing. So I have G to the number of boundary components modulo the diagonal action of G, which is giving me automorphisms of the whole structure. So the theorem in this case is saying that the derived modular envelope of G underbar is equivalent to the moduli space of surfaces with a principal G bundle. Arbitrary G bundle, yeah. Yeah, I haven't put a connection in. You could possibly try to make a version with connections.
These are discrete groups that you mean.
No.
You mean flat bundles, but when you say holonomy, it's either a flat bundle or...
Well, or it's defined up to some choice, so some space of choices.
Oh.
So the topology of the group can go in there too.
Oh, okay.
Okay, so now I'm going to answer Natalie's question. What do these things look like? Okay, so what is this modular envelope construction exactly? Well, I'm going to start off, I've been talking about the associative operad and things that lie over it. So d psi is always an operad over associative or A infinity. So the A infinity operad or the associative operad, these are non-sigma operads. So they come from the world where you can't permute the inputs. And when you think of them as an operad in the world where you can permute the inputs, then you're thinking of it as living there just by freely adding in all the permutations of the inputs. So I'm going to work where these things actually live in the world of non-sigma operads. So I'll write rib for the category of ribbon graphs. So objects are ribbon graphs. What are the morphisms? The morphisms are, well, the morphisms are generated by edge contractions. So the basic morphisms here are just contracting some non-loop edge somewhere. I should say non-loop. So those are the basic morphisms, but then those generate much more general morphisms. And the isomorphisms of ribbon graphs are also in here. The more general morphisms are surjective maps of graphs which have pre-images of vertices are trees. So it's morphisms which are allowed to move the graph by some isomorphism and then collapse some trees down to single vertices. So a non-sigma cyclic operad, I suppose I should say. A non-sigma cyclic operad gives a functor from this category of ribbon graphs to whatever category your operad is living in. For me, that's usually spaces. And it sends a graph gamma to the space of labelings I should have given my operad a name, P. So the space of labelings of vertices by operations of the appropriate arity of P. So for example, if I have something like this, I would get from this vertex on the left here, I get something of cyclic arity 3 crossed with something, I get the space of operations of cyclic arity 4. So I'm just getting the space of labelings of the vertices of the graph by appropriate operations in the operad. In fact, in Yuri Manin's talk yesterday, he mentioned this concept of generalized operads, where you sort of turn this around and you say an operad or a generalized operad is exactly a functor out of some variation on a category of graphs, which has a couple of extra properties that are easy to formulate. So you can think of an operad as a way of associating a space to a graph such that when you contract edges, the space behaves in a nice way. Okay, so that's the category of ribbon graphs. Now I need to tell you what this modular envelope is. Well, I've got space over here. So the derived modular envelope of my operad P in arity n is going to be, well, there's a way to motivate why this is what it is, but I'm just going to write down the answer. This is the homotopy colimit. So I'll write rib n for the category of ribbon graphs with n labeled legs. It's the homotopy colimit over the category of ribbon graphs of the functor associated with the operad P. Now, I need a slight variation on this category of ribbon graphs.
I'm a little confused. Is that a statement or a theorem? I mean, is that a definition or a theorem?
You can take it as a definition, or you can formulate a cyclic operad as a certain type of functor out of the category of ribbon graphs, and a modular operad out of a different category of graphs to which this one maps to. And you can say the modular envelope is the Kahn extension.
Yeah, okay.
Yeah, so you can take this as a definition or a theorem. And this thing forms a modular operad essentially because these categories of ribbon graphs with labeled legs form a modular operad by gluing the legs together. So I'm going to need in a few minutes something that I'll set up right now. So, all right, rib reduced inside rib. This is the subcategory of graphs with no bivalent vertices. So bivalent vertices are not allowed. Now there's the inclusion of the reduced graphs into the full category of all ribbon graphs, but there's also a functor going in the other way, which I call reduction or rho. Which just sort of irons out the bivalent vertices. So it would send something like this with the bivalent vertex here to the same graph where you just forget there's a bivalent vertex there and think of the whole thing as one edge. So I think of this as the reduction functor. Now, by properties of Kahn extensions, if I look at the homotopy colimit over the category of ribbon graphs with n legs of some functor p, which is going to be an operad here, this is equivalent to the homotopy colimit over the category of reduced ribbon graphs with n legs of the derived Kahn extension along this map rho of my functor p. I'm just setting this up because this process of integrating out the bivalent vertices is going to be important in proving the theorem. So what we're doing here is integrating out the vertices, the bivalent vertices. So P was a functor that really pays attention to bivalent vertices, and this Kahn extension along the reduction functor now has the effect of the bivalent vertices integrated out. And what I want to do is pay close attention to what's happening here. So let me
Is the order correct?
Hmm?
Shouldn't you precede the P by left concept? P is defined on ring, isn't it?
So the homotopy colimit of P along the bigger category is, sorry, I have a functor out of rib, and the homotopy colimit over rib is the same thing as sort of integrating along this, and then it's the Fubini theorem for homotopy colimits. Okay, so what's happening here? Well, a bivalent vertex is a cyclic arity 2 part of the operad. And so because you can take a string of bivalent vertices and contract edges in that, this is a monoid. And so when I integrate out these bivalent vertices, what I'm doing is building actually, it turns out, a two-sided bar construction for the monoid associated to a bivalent vertex acting on the left and the right side. So let me draw picture over here. So what would if this is my graph gamma, what would this con extension of P evaluated on gamma do? Well, I'd have I'd have P of 3 coming from this vertex. I'd have P of 4 coming from the right. But I don't have just the product. I have all those virtual bivalent vertices that I've integrated out in there. So this is crossed over the, it's the product of these mod out by the action in the homotopy sense of this monoid P2 in the middle. Okay, so now we come to the core of the idea here. So when Costello proved that the cyclic operad of moduli spaces of disks generates the whole thing, he did it by this very ingenious argument of taking moduli spaces, adding some boundary to them, and then doing a sequence of operations which sort of flow from the interior of the moduli space onto a piece of the boundary. And by repeating this operation over and over again, he eventually arrived at moduli spaces of graphs of disks. Now, I need something different because I don't have moduli spaces that have nice differential geometric structures that I can do flows on. And there's a lot of analysis that I personally am not very fond of. So I need a different route around. Now, it turns out the engine that makes this work for me is the idea of arc complexes on surfaces. And so, well, let me just put up a definition, and I'll tell you about this. So if sigma is a surface with boundary, an arc in sigma is an embedding from the interval into sigma such that the boundary goes into the boundary, and this is, if sigma has marked boundary, this is the non-marked part of the boundary. Now, A of sigma is going to be a category of arc systems. So the objects of this are just systems of arcs. They're collections of arcs in my surface with an extra condition. The arcs have to divide the surface up into disks. So if I cut the surface along the arcs, what I'm left with after the surface has fallen apart has to be just a bunch of disks. So those are the particular collections of arcs that I'm considering. The arcs have to be disjoint. They can't touch each other. They can't touch the marked boundary. I'm thinking of the objects as being discrete here, but this is going to be a topological category. So Hom from one arc system to another is going to be the space of pairs where it's the space of pairs where I have some alpha naught in alpha, so some subcollection of arcs. and an isotopy from alpha naught to beta. So this is a topological category. The objects are just a discrete set, but the morphisms have the morphism spaces have topology. So choosing a subset here, that's a discrete choice. But then once I've fixed an alpha naught, there's a space of isotopies from this collection alpha naught to beta. And so I really want the topology of the space of isotopies in there to make this work nicely. So this is the category of arcs. Let me just draw one example here. If I take this surface here, I can have, I can use colored chalk. I have one arc which starts here and goes around like that, and a second arc which starts here and goes through the middle and comes out the back. And if you have an arc system which cuts the surface up into disks, then you get a dual graph, which is a ribbon graph.
So an arc system is non-empty.
Yeah.
So if it happened to be a disk already, you still have to cut it somewhere.
Yeah.
Okay.
Yeah. So it turns out with disks, you can be a little bit flexible.
All right.
It doesn't actually matter whether you declare it has to be non-empty or not. Okay, so there's given an arc system, you have a vertex for each disk and an edge whenever two disks meet along an arc. So you get a dual graph. In this case, the dual graph, I've run out of space here. The dual graph looks like this. There's one circle and a second circle. And there's a ribbon structure, so you have to keep track of which order the edges come in at the vertex there. Okay. I'll just write A reduced for the subcategory where the dual graph is reduced. Okay, now here's a theorem. If you take the nerve of this arc category, or equally well, the nerve of the reduced version, that's contractible. So the fact that this arc category is contractible, this essentially goes back to Hatcher and whoever else proved that, several people have proved this, that the arc complex for a surface is contractible as long as the surface isn't something exceptional like a disk or an annulus. So the arc complex is made out of collections of arcs which don't necessarily divide the surface into disks. But by an inductive argument, you can show that the inclusion of this smaller thing of systems of arcs which do divide it into disks, that inclusion is a homotopy equivalence. And since the bigger thing, arbitrary collections of arcs, that's contractible, then the smaller thing, the collections which divide into disks, is contractible. So the idea of this theorem over here is to say that the space of surfaces is homotopy equivalent, because this space is contractible here. The space of surfaces is equivalent to the space of surfaces equipped with a decomposition into disks. And the space of surfaces equipped with a decomposition into disks and a psi structure is equivalent to the space of surfaces equipped with a decomposition into disks and a psi structure on each one of the disks such that the structures agree. But now, because of, where did I write it. Oh, I think that. Because of what this integrating out the bivalent vertices business, it turns out that you can make a direct comparison and see this. So how much time? I guess I have a couple of minutes to write this out. So it's kind of just a big diagram that you look at here. So if I take the collection of all diffeomorphism groups of surfaces, and I think of this as a category, then psi is a functor from this category to top. So this comes back to what John said. I want to make sure that psi is a continuous functor, that it's isotopy invariant. And the homotopy colimit of this functor is the moduli space. So the moduli space was the value of psi on a surface modulo the diffeomorphism group. So that's the same thing as taking the homotopy colimit of psi as a functor here. Now, I'll write this as a growth and deconstruction. So this is the category with one object corresponding to each surface, except I've spread that object out into a collection of objects, one object for each surface equipped with an arc system that breaks it up into disks. So this is the space of surfaces with the decomposition into disks. This map here is it's a homotopy equivalence of nerves, and I have something which I'll call psi bar here. So psi associates to the surface the space of structures on it. Psi bar associates to the surface with a decomposition to disks a psi structure on each disk such that the structures have a homotopy across each one of the arcs so that they're compatible up to a homotopy at each one of the arcs in the system. And the homotopy colimit of psi is equivalent to the homotopy colimit of psi bar. So there's a natural equivalence going from psi to psi bar by taking the structure and restricting it to all of the disks. Okay, now by taking the dual graph, you can go from the space of surfaces equipped with a decomposition into disks into the space of ribbon graphs without any bivalent vertices. And here, I'll write, I want the operad of moduli spaces of structures on disks, except I then integrate out the bivalent vertices. So what is the value of this functor on a graph? It's a disk for each vertex and a psi structure on each disk. And because of what I wrote here, the structure is trivialized along each arc, except then I've modded out by the action of the value of this on a bivalent vertex, which is the loop space on the space of structures on the space of germs of structures along an interval. So there's a transformation this way, which is a pointwise homotopy equivalence of functors. So the homotopy colimit of this guy is the homotopy colimit of this guy is the homotopy colimit of this guy, which is the modular envelope. And I'll finish there. Thank you.
If I remember right, the modular envelope is the monoidal left con extension, right? Not perhaps a monoidal functor from this category of trees or whatever it is. Isn't that right?
I mean, I can think of probably several different ways of defining it.
But in no way, it's never just a functor. So you need to take the monoidal left con extension rather than just the left con extension. Isn't that right?
Yeah.
So I guess it's the same here.
It turns out they coincide, yeah.
What's the reason?
I don't know if there, I mean, somebody else could probably tell you that there is a reason. I mean, for me, I just,
I can explain.
okay, yeah. For me, I just look and see that it works. Would you like to explain the reason? Is it something you can say quickly? Or?
Well, sorry, but
Okay.
there is a reason, but two categorical reasons behind this. What you construct is ribbon graphs. It's one of these internal algebra classifier, and that within this internal algebra classifier has this strange property that usual can extension automatically algebraic an extension, so it's trigger for symmetric monoidal functions and so on. But it's we have a paper now, it's kind of draft here, about 100 pages.
Okay.
I cannot do it quickly.
Yes?
So, just as a point of as preliminary to my question, as a point of terminology, this type of modular operator is a generalization of the older use of the term, because these are open-closed modular operads.
So I haven't mentioned any closed boundaries.
No, I'm about to.
Yeah.
But the original modular operads had only closed boundaries. That's
Well, the original modular operads just had some abstract kind of boundaries, right? I mean, if you want a particular example.
These are not modular operads in the sense of the original definition. They're in the sense of a generalized definition of open-closed modular operads. But now that brings me to my question, which is now if we allow...
So hold on a second. I thought the original definition of modular operad didn't...
if you like, I mean...
You're thinking of the example of moduli spaces.
No.
No.
I know what a modular operad
I know. I read your paper. That's how I know.
Your underlying cyclic operad is non-symmetric, whereas the underlying cyclic operad in a modular operad is symmetric.
Yeah.
It's a different theory.
So
it's a different sector.
I'm taking it. There's an underlying cyclic operad, which it comes from a
let me move
non-symmetric
on.
operad.
Yeah, so this is a different sector of a unified theory, but in Costello's work, he allowed closed
Well, he
sector.
yeah, that was when he goes to a two-colored version.
That's right.
Yeah.
So that's my
I haven't gone to the two-colored version yet, but the same sort of thing would work as long as you have some free boundary, some boundary which isn't closed and isn't marked, then you can do the same thing here. And so
Yes.
if there's a two-colored version with closed and open boundaries, then it would still be generated in this homotoppical sense by disks and annuli, where one of the boundaries of the annulus is a closed boundary.
And is the proof the same?
Yeah.
Actually.
Yeah. So in fact, I have a PhD student who's working on using that idea to then give some generalizations of Costello's theorem to topological field theories for, say, surfaces equipped with a principal G bundle. Yeah.
Is there a equivalent junction underlying that theorem? So are there model structures on cyclic and modular operads?
Maybe Clemens is the person to ask about this.
Yes, it is. Sure. But one has
It's again, it's not published version.
with one has to be careful. It's like for symmetric operads.
There
So
are
in general,
problems.
symmetric operads do not support a model structure. Only reduced symmetric operads.
From zero.
And for cyclic and modular operads, you have to be careful. But I think that the remark of Ezra is important, that there are different kinds of cyclic operads. So there are planar cyclic operads and symmetric cyclic operads.
Yeah.
And the theorems change.
Yeah.
Practically, if you
But given a planar
you
cyclic
change
opera.
from one kind of family of operads to another.
Yeah, so because I'm using ribbon graphs here, my cyclic operads are non-symmetric or planar. Yeah. But you can always do an extension, a con extension to get to a symmetric version.
What would be Ecofiber's replacement of tip psi as a cyclic operad?
Cool.
Such a thing?
W.
Yeah, exactly.
Okay, but that gives you another way of computing L.
Or I mean, Bruno would say take a bar-cobar construction.
But actually, he did it in the beginning of the talk, because this D or this yes, this D is actually a covariant replacement of the terminal cyclic operator. So to some extent, in the planar setting, or it's something which resembles to replace the terminal planar cyclic operator by this disks, these marked disks. This is some kind of, or it resembles the covariant replacement.
And that was unnecessary.
Can I make one last comment to the coherence of the workshop? As far as I remember, that to compute the homology of these guys, you can compute them. The other theorem says you can compute
Volume.
with a graph complex like Kontsevich, but the first one, the one that Alexander mentioned.
Yeah. So given any cyclic operator, there's a Kontsevich graph homology complex, and so if you have a cyclic operator O, then the homology, the O graph homology computes the cohomology of the spaces of the modular envelope of the causal dual or the derived causal dual of O. So these things are intimately related with these graph complexes. So that's more or less a result of Lazarev and Voronov.
Getzer and Kapranov.
Oh, sorry. So you didn't say it as inexplicitly as they did, but they were. I mean, they were more explicit than you.
You have to say things explicitly now.
If you want me to understand it,
Well, come on.
Explicit of me if you want. Okay, exactly.